Serverless computing. Serverless computing represents a revolutionary paradigm in cloud computing that allows developers to build and run applications without provisioning, managing, or scaling servers. Despite its name, serverless does not mean that servers are absent. Rather, it implies that the cloud provider completely abstracts away the underlying infrastructure management from the developer. This includes tasks such as server provisioning, patching, operating system maintenance, capacity planning, and autoscaling. The core idea is to shift the operational burden from the developer to the cloud provider, enabling developers to focus solely on writing code. No server management. The cloud provider handles all aspects of server provisioning, scaling, patching, and maintenance, freeing developers from infrastructure concerns. Event-driven execution. Functions are invoked only when a specific event occurs, rather than running continuously. Events can be HTTP requests, database modifications, file uploads, scheduled timers, or messages from queues. Automatic scaling. The platform automatically scales the number of function instances up or down, from 0 to thousands, to meet demand without any manual configuration or intervention. Paper execution model. Billing is based on the actual compute time consumed, down to milliseconds, and the number of invocations, leading to cost efficiencies for intermittent workloads. Statelessness. Serverless functions are typically designed to be stateless, meaning they do not retain any data or state between invocations. Any required state must be persisted externally, for example, in a database or object storage. Cold starts. When a function is invoked after a period of inactivity, the platform needs to initialize a new execution environment, which can introduce a small latency known as a cold start. Subsequent invocations on a warm environment are faster. Concurrency control. Developers can often configure the maximum number of concurrent instances for a function, helping manage resource usage and downstream service throttling. Integrations. Serverless platforms offer deep and native integrations with other cloud services, such as databases, message queues, API gateways, storage services, and monitoring tools, simplifying application development. Execution limits. Functions often have defined limits on execution duration, memory allocation, and CPU, encouraging developers to write small, efficient, and single-task functions. The underlying mechanism of serverless computing, particularly FAS, involves a sophisticated orchestration layer, managed by the cloud provider. When a developer creates a serverless function, they write their application logic in a supported language, for example, Python, Node.js, Java, and deploy it to the FAS platform. The platform then packages this code, along with any dependencies, and prepares it for execution. Initially, the function remains dormant, consuming no resources and incurring no cost. Web and mobile backends. Serverless functions are ideal for building highly scalable and cost-effective backend APIs for web and mobile applications. An API gateway can route incoming HTTP requests to specific functions, which then handle business logic, interact with databases like DynamoDB or Cosmos DB, and return responses. This is perfect for microservices architectures, where each service can be a serverless function. Real-time data processing. Serverless is excellent for processing streams of data in real time. For instance, an IoT device sending sensor readings to a message queue, for example, Kinesis or Event Hubs, can trigger a serverless function. Thanks for watching this training video. If this helped you, please like this video and subscribe to the channel for more content.